One of the most famous stories in science is the story of the apple falling on Isaac Newton's head. And so we question, what is the purpose of this story? Because it probably didn't happen that an apple just happened to fall on his head. And the purpose is not that he discovers gravity, because this happened in the mid-1600s. And so, of course, people before 1650s, we're talking about people like Galileo and Christopher Columbus and the Pilgrims, they knew that things fell down. So what's the purpose? Well, Isaac Newton also knew that things fell down. And so he got a little concerned because he looked up in the sky and he saw a much bigger object, the moon. And he wondered, do I have to worry about the moon falling down on my head next? And the answer is no. Well, why not? So to answer that question, he did a thought experiment known as Newton's mountain. He said, what if I take a cannon to the top of the tallest mountain I know, and I fire a projectile out of that cannon? Now, eventually fall and hit the ground. What if I fired a little bit faster? Well, again, fall and hit the ground. What if I continue to fire it faster and faster still? Eventually what's going to happen is this cannonball will circle the entire Earth and come around and hit us from behind. And the reason being is because not only does the projectile take a parabolic path, a curved path here, but the Earth is curved as well. And if those curves match up, the projectile will perpetually fall around the Earth. And that is what the moon is doing. The moon is perpetually falling around the Earth. Now, Isaac Newton did not stop there. He took it one step further. He said, what's so special about the Earth? Do other planets and moons pull things down? The answer is yes. We know that the moon pulls things down because we've been to the moon, and the rocket ships were able to land on the moon. Otherwise, without gravity, it would just continue to float away. And the people were able to walk on the moon. If there was no gravity, when they went up in the air, they would never come back down. So the moon has gravity. And likewise, the sun has gravity because the sun is able to do the same thing as the Earth does to the moon. It pulls it around the moon, or pulls it around the sun. And so anything that has an orbit to it is going to have a gravitational pull. So all celestial objects have a gravitational pull. Well, what about other objects? What about your baseball or your pencil on your desk? Do those have a gravitational pull? And the answer is yes. There's nothing special about the Earth. It's just that it's much bigger and therefore has a much more gravitational pull than that baseball. But if we were to get rid of the Earth and we were to go into deep space, well, then we would have the force. And that force is gravity. And so the baseball would come towards us just like it falls towards the Earth. It would fall towards us if there's no other gravitational force around it. And if we were to give it a push, we could even make it orbit us, just like the moon orbits the Earth. Now, he didn't stop there. He wanted to figure out the relationship between the Earth, the gravitational force of any two objects. And so he says that the gravitational force is proportional to the mass of the two objects. So if my two objects are the person and the baseball, I would take the mass of the person and the mass of the baseball. So bigger mass, more gravitational force. It's also dependent upon the distance we are away. But it's not just the distance. Through experimentation, he determines that's the square of the distance. It's an inverse square one. Think of it this way. If I get significantly far away from the Earth, I do not feel the attraction of the Earth. Like when I'm on the moon, I don't have to worry about the Earth's gravitation. I just have to worry about the moon's gravitation. But these units don't match up. We don't get newtons with these units. So they figured out there's a universal gravitation constant, which we use the capital letter G to designate. And if we multiply by this value, which is 6.67 times 10 to the minus 11 newtons times meter squared per kilogram squared, we arrive at our desired units of newtons. So this is a conversion to get us to the units that we want. So to recap here, Isaac Newton said all objects with mass are attracted to one another. The larger it is, the more traction there is. However, we only use this when we are not at the surface of the Earth. So if we are talking about being on the moon, then we might use this new formula that we just derived. This is usually used between any two planets, or if I'm going back and talking about the gravitational pull between myself and the baseball, then I'd use this new formula. Otherwise, if I'm talking about the gravitational pull from the Earth, and I'm near the surface of the Earth, then I will use that old formula. One last thing before we wrap up, and that is this letter R. This R is the distance between the centers of the two objects. It is not a radius. And Isaac Newton used his calculus, his integration, to figure out that it is between the centers of the two objects, not the front surfaces. It is between the centers, and more technically, it's between the center of mass. So that's for a later discussion, between the centers of the two objects.